next topic is optimization MEA performance with non-PGM catalysts. It's from the Chief Technology Officer from Pajarito Powder, Barr, Halevi. Give him a big hand, please.
Is this okay? Well, thank you, everyone, for coming. So let me see if this clicker works. There we go. Okay. Where do I point this? Okay. So I'm going to tell you a little bit about deployment of non-PGM oxygen reduction catalysts in PEM fuel cells. I'm Barr Halevi. My colleague Tom Stephenson is here. We're in New Mexico. So a little bit about myself, of course, and our company, a little plug, and then, of course, a little bit more information. First of all, what are non-PGM catalysts? A little bit about the technology that we're commercializing and the type of procedures that you would have to do to evaluate them internally. Okay, so our company was founded under the, basically to answer a simple problem that you're all aware of, that fuel cell catalysts are prohibitively expensive. There's lots of factors that go into that, and our approach was to look at new materials where platinum was no longer an issue, and then of course we looked at manufacturing practices for making these materials. They needed to be done in a scale that was appropriate for today, and that could be scaled to future needs when they became present. Okay. There we go. So where we are a year and a half later is that we were able to make a number of catalyst formulations where we can tune them to individual catalyst requirements, back pressures, relative humidities, and so on. And then, of course, we were able to scale them to the 50 and 100 gram levels, which is what we need today, not tons. Okay, done with the public relations part of the talk. So the type of non-PGM oxygen reduction catalysts I'm describing today have been investigated and developed by a number of groups out there. Right here, I'm mentioning 4 groups, the Dodele group, Zelenay group, Atanasov, and Mukherjee. All 4 of these groups, as well as others, talk about ways of developing non-PGM oxygen reduction catalysts. And really, when you look at them, even though they can be made different ways, they all have a very similar type of active site that is described. And it's this iron that's attached to nitrogens and to carbon. Now, different groups think those are different ones, whether they be pyridinic, 2 nitrogens, pyrrolic with 4 or 3. They may be between layers of carbon at the edges. That's not quite clear. But what is clear is that in an actual catalyst, when we do XPS, for example, to understand what's really in there, there's a mixture of all of those. It's really hard to deconvolute exactly what's in there. And so today, we don't know exactly. However, when you look at the physical structure of the catalyst, right, so here you can see a TEM of a bulk catalyst. It's very basically carbonaceous and graphitic. If you zoom in, you can find edges of particles where you have stacks of carbon. So really this idea of having either pyrrolic or pyridinic edge type effects is all consistent. Okay, so the catalyst I'm going to be describing today are made using what is called the sacrificial support method. Here we prepare the precursors, mix them with a sacrificial support that we then take out, pyrolyze, etch the sacrificial support away, and then do a second pyrolysis to clean it up. And what this allows us to do is to create a hierarchy of porosity within the catalyst. So we start with, for example, silica, infuse the precursor, pyrolyze it. Once you've pyrolyzed it, you create nanopores and really some sub-micropores just from the decomposition of the materials. And then we can etch away the silica, leaving this very tailored porosity, leaving a self-supporting catalyst, right? So some other technologies rely on building a catalyst on top of a carbon support. Here you're building a self-supporting catalyst. And let me show you a little bit more of, this is kind of a small screen. Okay, so where the sacrificial support becomes really helpful is that you can obtain different sort of structures of oxides or sacrificial supports. So for example, if you get a precipitated silica, you can get things that are in the order of anywhere between 10 and 40 nanometers, but then they're agglomerated, versus a fumed silica that has more of a chain-like dependence. And of course, I was very fortunate to find an image that was made of a typical platinum and carbon catalyst where you can see almost an identical structure and very much the same features. But what we can do with a sacrificial support is tailor the silica all the way from 5 to about 50 nanometers. Okay, so this is the catalyst that we've worked mostly on. And you can see here in an SEM, okay, maybe you can see here in an SEM, that there's 3 levels of pore size distributions. There are things on the 1 to 2 nanometer. Then there are things that are more on the 10 to 20 nanometer, which corresponds to the primary particle size of the silica. And then, of course, the agglomerates. And again, with the TM, okay, there's something there. You can't really see it. Rotating disk electrode shows you that we're talking about 0.78, 0.79 volts for halfway potential. Can you guys see any of the structure within that SEM? Okay, so I'll come by the booth. I'll display this on a better screen. Okay, so a very simple way of making electrodes, and there are people in this audience who know how to do this much better than I, but this is an approach where you can take the sample and make a simple GDE that should work pretty simply. Okay. The method I'm going to describe is highly repeatable. If I take 3 different batches, make a GDE out of them, you'll get pretty much the same performance. Okay, so for the ink composition, catalyst, ionomer, solvent, we chose a spray method as a way to do this. And if you do that, you want somewhere on the order of 3 to 5 weight percent of solids, water, IPA, or some other low boiling point solvent. Ionomer to catalyst ratio is very critical for these materials. It's a little bit higher amount than what you would get for a normal unsupported catalyst. And we find that something around, depending on really your back pressures and your oxygen, and I'll discuss that later, but you do need a little bit more. Okay. Because we do we're essentially a scale-up from university technologies. You know, universities like using sonic baths and sonic horns versus something like a homogenizer that works better. Use a homogenizer, use a shear mixer. The sonic bath just doesn't really work, and that shows you as you sonicate it, gives you some performance, sonicate it more, doesn't really help. Throw a homogenizer in there, and now you're fine. Okay, so this is an effect of mixing at different shear rates. If you mix this too much, you start degrading the ink. So really, 18,000 RPM using a 20 millimeter rotor is about what you would do. So it is possible to overmix these. Okay. I mentioned the Nafion content is a critical aspect here, and that's really the case. So as we move from a 40 to 50 to 60 weight percent Nafion, you can see, in the area that we really care about, we're getting better and better performance, but we're starting to really impede transport. So this is a very simple construction, and you can, of course, do a little bit better by just adding some carbon. This is apparently something that's well known in the industry, and people were kind enough to share that with us. Okay, so here's where we start looking at oxygen versus air, and you can see here this is not as clear of a chart as I should have shown you, but in the blues we're seeing 40 weight percent Nafion, air, and oxygen, and then 60 weight percent again air, and oxygen. And you can see that once we move to air, we're really starting to get transport issues. That's a little bit clearer here using a 40 weight % sample where as you go from half to 1.5 bar back pressure, you're really starting to get performance. And if you really go to, let's say, 4 atmosphere, you're starting to approach what you see for oxygen. So the transport structure of these catalysts needs to be improved. And then, of course, for oxygen. Okay. The ink deposition ends up being, again, you all know this, but for a very simple way to do this, ink deposition is very important and how one does that. A very simple thing that any graduate student can do, any technician can do within a day or two is just a airbrush, right? And here you heat the GDL to about 70 degrees C, you spray it about 1% per pass. That's a fairly heavy spray, I'm told, but it gives you a fairly good sort of rate of drawing in connectivity between the layers. Catalyst loading. These are less active than platinum. Therefore, you need much thicker coatings and much thicker layers. As you go to higher and higher loadings of catalyst, you eventually start impeding diffusion. And so there's really a sweet spot of around 1 to 1.5 milligrams per centimeter squared. And that's pretty much universal for any sort of testing conditions. You know, whether it be half a bar of oxygen or 1.5 bar. Okay. Pressing is also important because these are larger particles than platinum catalysts. You have to be a little bit more careful not to overpressurize them. 500 kPa per centimeter squared, 131 C, soak for 6 minutes. You can, of course, increase the temperature or lower the residence time depending on what you're pressing in there. This is optimized for paper GDLs. Testing. This does not require the break-in period that you need to get optimal performance out of platinum catalysts. Throw it in there for 10 minutes at 0.3 volts to help humidify and get everything going. Cycle it 10 or 20 times, and that's about what you're going to get for stable performance. Okay, so the big question, of course, is what do you get out of this? So here is our non-precious metal catalyst compared to a commercial anode. So this is a complete electrode that I buy from Johnson Matthey, from Alpha Azar, 0.2 milligram platinum per centimeter squared. And you can see at the kinetic regime, you're talking about 550 or so millivolts, versus for us, we get about 100. So what does that mean? This is the catalyst that gives you about 100 milliamps at 0.8 volts. If you go ahead and you make a volumetric correction out of that, you're somewhere between 2 and 400 amps per centimeter squared, per centimeter cubed, depending on what assumptions you make in terms of the density of the material and the thickness of the layer. Okay, durability, all right. That's really been one of the big issues for these catalysts. We are the scale-up partner for a Department of Energy program. Under this program, a number of characterizations were done, including what's called a start-stop carbon corrosion test, where you cycle the material between 1 and 1.5 volts. You do that 1,000 times, and it corrodes like crazy. So here's a platinum, 15 milligram per centimeter, 0.15 milligrams per centimeter squared catalyst. And after the corrosion protocol, it's lost a huge amount of its activity. It's this blue line. Versus our catalyst, which starts at this red, of course, much lower performance, but percentage loss is similar, right? So we're talking about the same durability. Of course, it's less active at the end, less active to begin with, so you have to have more of it. In terms of the electrochemical surface area, you actually start getting some capacitance buildup, right? So as we go more and more and more, we're getting more. An interesting question that was asked was, what is the degradation mechanism, right? So the understanding is if you have platinum on carbon, you're burning the carbon away, platinum goes away. That's a fairly well-studied mechanism, and there are ways around it. This is a very different material. It's not really supported. So what's causing that? And so far, really, what we have mostly is this XFs that shows you In these two features, you have the iron-nitrogen feature, and then you have an iron-iron feature. Now, what's happening essentially is the iron-nitrogen is decreasing, and the iron-iron is increasing. So it seems like we're making some iron nanoparticles, and that's the degradation mechanism in this case. So there are ways of doing, so durability under start is similar to platinum carbon, but of course it's not nearly as active to begin with. But it does work. Okay, that's it. I wanted to thank you for your attention. I want to thank the other members in this team, the University of New Mexico, the guys that developed this catalyst and were very helpful in letting us license it and helping us scale it up. Department of Energy, Northeastern University, Michigan State University, and the Nissan Technical Center in North America were all part of this. And of course, the Verge Fund, who pays our bills. And with that, I'd love to entertain any questions you may have.
And I like to thank you for this interesting presentation. Yes, are here some questions?
Thank you for the presentation. You said that you use more catalyst, or you use more of your material.
Correct.
Do you have comparison of the thickness that is versus a standard platinum?
It's a great question, right? So if a platinum carbon catalyst is 0.2 milligrams per centimeter squared, let's say what state of the art is 60 weight percent platinum or so, so you're talking about 0.3, 0.4 milligrams per centimeter squared of catalyst. For our case, we're talking more like 1.5, so factor 4, call it. The problem really becomes here, one of those things you learn when you're a catalyst developer and you say, oh, I can make an MEA, and then you understand why people are very sophisticated and very complex in how they make MEAs, right? It's how you compress it. The rate of spraying of these things make a difference, right? How it compacts as it shrinks and so on. So you can make these GDE layers anywhere between 40 and 100 microns,
Okay.
depending on how thick you do that.
Okay.
And then, of course, once you compress them to put them into an actual cell, that changes.
Okay.
So that's it's a little complicated of an
40
answer there.
to 100. Okay. Thank you.
Hi, do you have any steady state durability data? So you showed the cycling, but you have for steady state and any variations on that depending on conditions?
Okay. So we have load cycling, and we have a week here, a week there at a time on these materials, and it's pretty stable under those conditions. That's why we've resorted to the accelerated stress tests as doing that. I don't have them right now, and we don't really have anywhere on the hundreds or thousands of hours that really need to be done in order to prove that a catalyst like this works. The same, we do have report data for essentially a load cycling that shows actually reasonable durability as well. There's some loss, but not the same as platinum. But no, I don't really have any sort of constant hold.
Hi, thanks. There are two questions here. The mass transfer effect, what you could see in the data, is that, mass transfer effect, what you could see in data, that is because of the thickness of the catalyst layer there?
It could be due to two or multiple reasons. One is just the sheer thickness of the catalyst layer. It can also be, right, if you remember, this catalyst has internal porosity, right? So that has both good things and bad things. We have been able to show that by using larger particle silica, we can decrease that effect. So it is a true mixture of the thickness of the catalyst layer and the internal porosity of the catalyst.
And the second question, you started your presentation with the cost. Can you compare the platinum cost and the catalyst here used?
Okay. So I have a price that you can buy it today, which is at the prototype stage. Platinum will always cost as much as platinum does, right? It may get cheaper, but it'll never be cheap. The materials that go into making our catalysts are ones that you can buy by the train load in any country. Processing is complex and There's lots and lots of steps to it, but it's all something that any chemical manufacturer will know how to do. At scale, this can be extremely, significantly less expensive than any platinum catalyst, even if you take, let's say, recycling into effect, because the chemical processing is really not that bad. So it's hard to make that direct comparison, right? There's that big question that always comes up. At what point does it make sense to take a catalyst that is less performing, but also much less expensive? And there's a study that was published in 2005 as a GM and Hubert Gasteiger, and the Department of Energy uses that now as their guideline for when that makes sense. And that is 300 amps per centimeter cubed is the performance level, and about 0.1 amps per centimeter squared at 0.8 volts, which this catalyst meets. And I believe it's the second one to meet. So it's a complicated question you're asking.
Yeah, that's it.
Thank you very much for your time and your interest.
Yeah. If they're coming maybe some question a little bit later in your mind, please do not hesitate to come to your booth. It's quite close to here. It's right over there. It's D80/1. And I think Halevi will welcome you and discuss any topic with you directly, face to face. So thank you very much for your attention.